Hello everyone, welcome to EEEE Lecture number 43B. Today we'll be talking about transformer losses. Alright, so there are some losses in the transformer, and the main two losses are as follows. They are called as categorized as copper loss and iron loss. So let us see them in detail now. Let us investigate what are these losses. So copper loss, also called as WCU, okay. A transformer windings are not ideal. Okay, in a practical transformer, the windings are not ideal. Every winding has a resistance. So you see these two windings, primary winding and a secondary winding. So these windings have small resistances. So this will have small resistance. This will have some resistance. Okay, that is called as winding resistance. Now, because there is a winding resistance, whenever a current passes through a resistor, there is a drop, voltage drop. And that loss that takes place due to winding resistance is called as a copper loss. Now, why the name copper loss? As the windings are made up of copper. Alright, hope it is clear. So, let us say that R1 is the resistance of the primary winding and R2 is the resistor of the resistance of the secondary winding. So, the primary, let's say we can write it over here, primary copper loss will be given by I1 square into R1 watts. Okay, let us call equation number 1. Then secondary copper loss will be given by I2 square into R2. You see, the current flows to the primary winding, and that current we call it as I1. Okay, and here a current flows through the secondary winding also, and that current is called as I2. So that's why the loss, or this is the power loss, right? Because there is a resistance, there will be a loss. So primary copper loss is denoted as I1 square R1. Secondary copper loss is called as I2 square R2 watts, and this is equation number 2. So what is the meaning by total copper loss? Total copper loss will be denoted by WCU, which is I1 square R1 plus I2 square R2. Alright, and this is also measured in watts. Let us call it equation number 3. I hope it is clear to you. Okay, so from the above equations, it is clear that the copper loss varies with the square of the current. Okay, if the current increases, the copper losses also are more. Alright, so this is about the winding resistance and the copper loss associated with it. Now, next we talk about the iron loss or the core loss, which we denoted by Wi. Now this is the construction of the transformer. This right hand side we have drawn. This is my iron core, okay, core of the transformer, and I am linking the primary winding and the secondary winding. They have been linked by the magnetic flux. Okay, so basically the loss is also associated with the core itself of the transformer. So let us see. Due to applied AC voltage, an alternating flux is produced in the core, and that alternating flux is called as phi. Alright. When any magnetic material is placed in the alternating magnetic field, hysteresis loss and eddy current loss takes place. Okay, now these are two new terms. We have first hysteresis loss. Let me add like this: hysteresis loss and eddy current loss. So these are two new terms. Let us see them, investigate one by one. The hysteresis loss and the eddy current loss takes place inside the magnetic core uh, of a transformer. Okay, so kindly note it. So this hysteresis loss plus the eddy current loss is your core loss or your iron loss. Now these two losses are together called as core loss. Okay. Now since the core is made up of iron, it is also termed as iron loss. Alright, so this is what it is about the iron loss, and the core loss is proportional to the applied voltage. Now normally the applied voltage is almost constant, therefore the core loss or the iron loss remains constant for all loads. Alright, Now, in order to understand, the hysteresis, the loss due to hysteresis current, and the loss due to eddy currents, we will be investigating hysteresis loss. So, since the supply to the primary is alternating, that is V1 is a AC signal, the core gets alternatingly magnetized and demagnetized, causing a loss of energy. And this loss is called as a hysteresis loss. I hope it is clear. And this loss is given by, now this is not derivable, WH, hysteresis loss in watts, is given by eta B max raised to 1.6 FV, and the unit is watts. So what is B max? B max is the maximum value of flux density in Tesla, F is the frequency of magnetic reversal, V is the volume of the material, and eta is the Steinmetz constant. Okay, so this law, we don't have to go into detail of it, or either the derivation is not there. So this hysteresis loss can be minimized by selecting the material for the core that has a low hysteresis coefficient. This is also, eta is also called as a hysteresis coefficient. So I mean, we cannot completely remove the hysteresis loss, but we can minimize it by selecting the proper material for the core. And normally we select steel material for the core. Okay, steel grade. All right, this is about the hysteresis loss. Now let's talk about the eddy current loss. Now, this loss is due to eddy current induced in the transformer core. Okay, you remember in the transformer core you have alternating flux which is linking the primary and the secondary winding, right? So we have, due to this alternating flux, there is also eddy currents induced in the transformer core, and this loss, it is seen in the form of a heat in the core. Okay, it is seen in the form of a heat in the core. So this loss is given by WE, which is given by K B max square F square T square V, and eddy current loss is measured in watts. K is the eddy current coefficient, B max is the maximum value of flux density, T is the thickness of the lamination, F is the frequency of the phase reversal, and V is the volume of the material. Okay. Now, let's investigate how to reduce or minimize this loss. So this eddy current loss can be minimized by using laminated cores. Okay, this is very important. We have shown you the transformer construction in the last lecture using laminated cores. Okay, so instead of having I'll explain over here. Oh, sorry. Instead of having a one single core like this, what we do is we take laminated core. So this is your single hardcore core. Now what we do is like this. We take the core and we take in the form of a sheets. Yeah, this is what is laminated core. So we have a one slice of it joined with the second slice, third slice, fourth slice. So this is what do you mean by laminated core. Okay. Now let's understand what is this eddy current coming from. When a magnetic material is linked with the alternating flux, EMF is induced in the magnetic material itself. It is as per the Faraday's laws of electromagnetic induction. This induced EMF circulates a current in the body of the magnetic material. Okay, this induced EMF circulates a current in the body of the magnetic material, and these circulating currents are called as eddy currents. Now the magnetic material is the winding and the core itself, right? And we have a alternating flux linking the primary and the secondary winding. So here is my so we have a primary winding, we have a secondary winding, and we have a alternating flux due to alternating voltage applied. All right, and therefore this gives rise to a circulating current which is called as a eddy current, and because of this eddy current there is eddy current loss which is given by this formula. All right, so if they ask you in the exam about various losses in a transformer, you have to explain about, let me go back over here. You have to start with copper loss, explain what it is, its origin, how to reduce it. We have to talk about iron loss or core loss, right? And then we have to talk about the hysteresis loss and the eddy current loss. So normally this question will come for 10 marks. If it comes for 5 marks, explain eddy current and hysteresis loss in brief, okay, and how to reduce each of them. Alright, this is clear. Can we move on to the next topic now? Alright, okay. Now, next we study about the transformer parameters. Alright, the transformer parameters are R1, R2, that is winding resistance, a practical transformer. Then we have leakage reactance X1 and X2. We'll see what is leakage reactance and what is Z1 and Z2. We'll see that in short time from now. Alright, let's proceed now. So winding resistance, as we have seen in a practical transformer, there is some resistance of the primary and the secondary winding. All right, because these are not a pure inductive coils. There is some coil resistance also, winding resistance also, which is denoted as R1 and R2 in this transformer symbol. Okay, so this is the transformer with the winding resistance shown as R1 and R2. Okay, R1 is the primary winding resistance, R2 is the secondary winding resistance. All right. So the resistance R1 and R2 of the two windings can be transferred to the either of the two windings. Okay, the advantage will be like the calculation will become very easy and simple. Now let us understand what does it mean. What does this mean? Okay, so let's say that we have drawn over here R1, R2, and here it is my V2. This is E2, E1, this is current I1, this is current I2. So let's say that we want to transfer the resistance of the secondary to primary. Alright, and why do we do that? Because the calculation becomes very simple and easy. So how do we do that? Let's do it over here. So if you want to transform the secondary resistance, secondary winding resistance into primary, so this is the technique. We draw R1 and R2 also. Okay, let me complete the diagram. Alright, so this is my V2, mutually induced EMF E2, primary voltage I1. Alright, and this is self induced EMF E1, and the current flowing over here is I1. Now what has happened is, if I want to transform R2 secondary winding resistance into primary, then this new resistance is called as R2 dash, and that is given by R2 upon K square. Alright, so whenever you want to transform, I mean, it can be proved that a resistance R2 in the secondary is equivalent to R2 upon K square in the primary. Okay, so R2 dash will be R2 upon K square. So the value of R2 upon K square is denoted by R2 dash. And what is R2 dash called as? It is the equivalent secondary resistance as referred to primary. Again I repeat, what is R2 dash? R2 dash is equivalent secondary resistance as referred to primary. Alright. Now this R1 and R2 dash, we can write it as a combination as one resistor R01. So R01 will be R1 plus R2 dash, and R2 dash is R2 upon K square. So R01 is R1 upon R1 plus K, R2 upon K square. Where R01, now what is R01? R01 is the equivalent resistance of the transformer as referred to primary. Alright. So this technique is called as a shifting of winding resistance to primary. So with this will be no secondary winding resistance, entire resistance will come over here. So this will be easier for calculation purposes. Now if this is the case, then the copper loss will be given by I1 square into R01. Now R01 is the series combination of R1 and R2 dash. Okay, is this clear to you? This is how we shift the winding resistance to primary. Then similarly we can shift the primary resistance to the secondary also. Now let us see that further. Similarly, it can be proved that the resistance of R1 in the primary is equivalent to K square into R1 in the secondary. Okay, so what we want to do, any primary winding resistance we want to shift it to the secondary winding. Okay, how do we do that? Let me draw the primary winding of the transformer and the secondary winding of the transformer. So in the secondary winding you will have an additional resistor in series with R2, Let me write the primary voltage as V1, self-induced voltage EMF as E1, mutually induced EMF as E2, and load voltage or the secondary voltage is V2. All right. Now let me add over here. Now this, when it transform, when R1 gets transferred to the secondary, it is called as R1 dash, and this is given by K square into R1. We are not going to prove that why how that happens. That's why it is written over here. It can be proved that a resistance R1 in the primary is equivalent to K square into R1 in the secondary. Okay, so that's what we have to remember, that whenever any primary winding resistance is been transferred to the secondary, it's multiplied by K square. All right. And what is this K? K is the transformation ratio. So value of the K square into R1 is denoted by R1 dash, right? And what is R1 dash? Equivalent primary resistance as referred to secondary. Okay. Now since it is referred to secondary, it is the equivalent primary resistance as referred to secondary. And the combination of it, the combination of this R1 dash and R2 together, we can call it as RO2, and RO2 is given as R2 plus R1 dash. And what is R1 dash? K square R1. So RO2 is R2 plus K square R1. And what is RO2? RO2 is the equivalent resistance of the transformer as referred to the secondary. RO2 is the equivalent resistance of the transformer as referred to the secondary. Alright. So the copper losses will be given by I2 square. Now there will be a current flowing over here. This is I1 and this is I2. So the copper loss will be I2 square into RO2. Okay, I2 square into RO2. I hope this is clear. RO2 is the series combination of R1 dash and R2. Alright, so this is about shifting the winding resistance to the secondary winding. Now, let's talk about leakage reactance X1 and X2. Leakage reactance. So, remember, in an ideal transformer, it is assumed that all the flux produced by the primary winding links both the primary and the secondary winding, and this flux is an alternating flux shown by this orange color box, and this is the flux phi. This is the iron core, this is the primary winding. Okay, due to the applied AC voltage V1, primary current flows, alternating current flows I1, and due to the electromagnetic laws of Faraday's law, we have self-induced EMF and mutually induced EMF, E1 and E2 respectively. So phi is the main flux linking the primary and the secondary winding. Alright. In practice, all the flux linked with the primary does not link with the secondary. Now this was an assumption, right? What was the assumption? The entire flux at the primary side is linking towards the secondary, which is not true. So as shown in the figure, some part of primary flux phi L1 completes its part by passing through the air rather than around the core. Okay, so this is as shown over here, phi L1. Similarly, we have phi L2. These are the leakage flux. Okay, so flux phi L1 is the primary leakage flux which links the primary winding and does not link to the secondary winding. It links itself. Okay, primary winding. Similarly, phi L2 is the secondary leakage flux which links with the secondary winding and not with the primary winding. So we have additional leakage flux which is phi L1 and phi L2 in addition to the main flux phi. Now what does this mean? The flux phi which passes through the core and links both the windings is called as the mutual flux phi. Okay, so this is the mutual flux phi which links primary and secondary winding, both of them. So the EMF induced, EMF induced voltages E1 and E2 are caused by the main flux. So remember that the EMF induced EMF E1 and E2 voltages are caused by the main flux. So flux phi L1 is in time phase with I1 and induces an EMF EL1 in the primary but not in the secondary. Okay, so this phi L1 will induce a EMF EL1 and this phi L2 will induce a EMF EL2 in the secondary winding. That's what you have written over here. Yeah. So phi L1 is in time phase with I1 and induces an EMF EL1 in the primary but not in the secondary. Flux phi L2 is in time phase with I2 and it induces an EMF EL2 in the secondary but not in the primary. Okay, the leakage flux linking with each winding produces a self-induced EMF in that winding in terms of EL1 and EL2. Okay, and that is equivalent to a small inductive coil in series with each winding such that, okay, so EL1 is given by I1 into X1 and EL2 is given by I2 into X2. Okay, because why is EL1 and EL2 coming? EL1 is coming due to flux, leakage flux phi L1 and phi L2. All right, so here X1 and X2 are known as the primary and the secondary leakage reactants. So this is just presenting the effect of the leakage flux. So X1 and X2 are representing the leakage reactants. Okay, because there is X1, okay, I1 into X1 is my EL1, and because there is X2, I2 into X2 is EL1, and this EL1 and EL2 is coming from this leakage fluxes at the primary and the secondary winding, that is phi L1 and phi L2. So to represent its effect, we have marked over here the transformer with the leakage reactance, that is X1 stored in the primary winding and X2 stored in the secondary winding. All right, X2 and X1 are the fictitious quantities. They are introduced for convenience to represent the effect of primary and the secondary leakage fluxes. Okay, so X1 and X2 will represent the effect of the primary and the secondary leakage fluxes. That is very, very important to understand. Okay, so this leakage flux is represented by X1 and X2 in the primary and the secondary winding. All right, now if I combine the winding resistance with the leakage resistance, I get this diagram, right? R1 X1, R1 is the primary winding resistance, X1 is the primary reactance in the primary winding. Then R2 and X2, R2 is the secondary winding resistance, X2 is the reactance of the secondary winding. So this is the transformer symbol with the winding resistance and the leakage reactance. Let me also mark the current. This is current I1 and this is current I2. Alright, so this is the transformer symbol with the winding resistance and a leakage reactance, and this is what happens in a practical transformer also. We have certain amount of winding resistance and leakage reactance also. Now let's talk about impedance. Now if I combine these two, R1 and X1, this will become impedance. This we can call it as Z1. Okay, and R2 X2, they are in series, we can call it impedance Z2. Now in a practical transformer, winding have some resistance R1 and R2. Also in a practical transformer, there is some leakage flux present near the primary and the secondary winding. So the effect of the primary and the secondary leakage flux are represented by reactance X1 and X2, which we have already discussed. Now the primary impedance, that is Z1, will be given by, it's like in rectangular form it is given by R1 plus J X1. So let me write Z1 is R1 plus J X1. But if I want to write its magnitude, Z1 will be given by square root of R1 plus R1 square plus X1 square, and that is in ohms. Okay. Similarly, secondary impedance Z2 is a combination of R2 and X2. So Z2 can be written in rectangular form as R2 plus JX2, and its magnitude will be given by square root of R2 square plus X2 square. Alright, so these are the primary and the secondary impedance. Now let's say that this equivalent resistance of the transformer, okay, if I want to shift the parameters of the secondary to the primary side, how will I do it? Anyone remembers? So if I shift any parameter from the secondary to the primary, I have to divide by k square. Remember, I have to divide by k square. So let us do that. In this transformer, we have R1 X1, R2 X2. I want to transform this R2 X2 into primary side. So how will I do it? Let me draw it over here. First I'll draw R1 X1, then we will have, let me complete the diagram. This is your primary winding and secondary winding parameters have been transferred to the primary. So this is my V2, mutually induced EMF E2, E1. This is my primary voltage V1, and then the current flows through it. It is I1. So R1 X1 is no problem at all. This is E1 E2 and we have V2. So whenever I've said that before, whenever a secondary parameter has been transferred to the primary, it is divided by k square. So this will be R2 divided by k square, and this will be X2 divided by k square. So R2 divided by k square is called as R2 dash, and X2 divided by k square is called as X2 dash. Okay. So now the equivalent resistance of the transformer as referred to the this primary, the equivalent resistance will be R1 plus R2 dash, right? So I can write it as RO2 RO1. Basically it will be R1 plus R2 dash. Okay, series combination of resistance will add. So this R1 and this R2. So it will be R1 plus R2 upon K square. Alright, this is RO1. Similarly, the equivalent reactance of the transformer as referred to the primary is given by X1 plus X2 dash. Okay. So we call that reactance as XO1, and this is X1 plus X2 dash. This is X1 plus X2 upon K square. Okay. So that is what we mean. Next, the equivalent impedance of the transformer as referred to the primary. The equivalent impedance, now let me draw and show it to you once. So this is what I meant. The primary coil or the winding and the secondary winding. So when the secondary parameters have been transferred to the primary, in the secondary winding we don't have anything. So here is the mutually induced EMF E1, self-induced EMF mutually induced EMF E2, self-induced EMF E1. Then we have a primary voltage V1. All right, and these two resistances are R1 and R2 dash. This is X1 and X2 dash. So the combination of these two, we call it RO1, and the combination of these two we call it XO1. So what is RO1? Equivalent resistance of the transformer as referred to the secondary. What is XO1? Equivalent reactance of the transformer as referred to the secondary. And if I combined RO1 and XO1, I'll get ZO1. And what is ZO1? ZO1 is the equivalent impedance of the transformer as referred to the secondary, primary. So ZO1 will be given by RO1 plus J times XO1, and its magnitude will be given by ZO1 will be given by square root of RO1 square plus XO1 square. I hope it is clear to you. Right? RO1 plus JXO1 is in the form of rectangular coordinate, and ZO1 is the magnitude of it. So it is square root of RO1 square plus XO1 square. Alright. Now we have shifted the parameters. In the last discussion, we have shifted the parameters to the primary side. Now we want to shift the primary parameters to the secondary side. Okay. Now, as we have discussed before, whenever we transfer any parameter from the primary to the secondary, it is multiplied by k square. Alright. So this is the transformer symbol with the leakage reactance and the winding resistance R1 and R2, and the leakage reactance X1 and X2. Now we want to shift the parameters to the other side. So let's draw it now. So at the secondary winding we will not have anything. Here we have a primary voltage V1, current I1, self-induced EMF E1. So here we will draw the secondary winding. So we have R2 Now R1 has been transformed to the secondary, so it will be called as R1 dash, which will be given by k square into R2. Then we have x2, this is x2, and next we have this x1 has been transformed to the secondary, so it is called as x1 dash, and we denoted by k square into x1. So here is my secondary winding, load voltage or the secondary voltage V2 and E2. Alright, this is how we transform any primary parameter to the secondary. Alright, and here also similarly, the equivalent resistance of the transformer referred to secondary is called as, this we can call it as RO2. Now the equivalent, so that is what we write over here, RO2 is basically R2 plus R1 dash, which is nothing but R2 plus K square R1, because R1 dash is denoted by K square R1. The equivalent reactance of the transformer referred to the secondary is given by X2 plus X1 dash, that is XO2. So XO2 will be X2 plus X1 dash. And what is X1 dash? X1 dash is K square into X1. So XO2 will be X2 plus K square into X1. Alright, and when we combine these two, RO1 and XO2, we get impedance ZO2. So the equivalent impedance of the transformer ZO2 will be given as RO2 plus J XO2. Now this is in the rectangular form. If I want to write the magnitude of ZO2, it is given by ZO2 is equal to square root of RO2 square plus XO2 square. Okay. So that is how we write the various formulas, and this is about shifting of parameters to the secondary side considering the winding resistance and the leakage reactance. I hope this topic is clear to you. Alright, so let's move on to the next one. Remember the unit of RO1 is ohms, the unit of XO2, RO2, RO1, XO1, XO2 is ohms. Even the unit of ZO1 and ZO2 is in ohms. So this is all in ohms. Alright, let's move on to the next one now. Let us discuss about transformer on no load. Now what do you mean by transformer on no load? A transformer is in no load when its secondary is open. Secondary is open circuited, that is I2 is 0. Okay, so this is my transformer core. Then we have this magnetic flux linking both the primary and the secondary winding. Here the orange color is my primary winding, green color is my secondary winding. Due to alternating voltage V1, your current, primary current flows I naught, right? And here E1 is the self-induced EMF, E2 is the mutually induced EMF produced. So under such condition where I2 is 0, secondary current is 0, the primary current I1 has to supply for the iron loss in the core and the copper loss in the primary winding only. Remember, in a transformer there are two types of losses, iron loss and the copper loss. Now since it is under no load condition, your secondary is open, so I2 is 0. That means the losses associated with the secondary will not be there. So the primary current I1 has to supply for the iron loss as well as the copper loss. Alright. So now the primary winding has some resistance. Therefore, no load primary input current I1 lags it behind. Your no load primary input current I0 lags it by the angle of phi naught equal less than or equal to 90 degree. Okay, so it will lag behind V1. Okay, it will lag, I have written over here lag it, but it lags behind V1 by an angle phi naught less than 90 degree. Alright, because it's a winding and it's an inductive winding or inductive coil. So the current will lag behind the voltage by less than 90 degree. The primary current I0, let's say the primary current I0 is the no load current. Under no load condition can be split up into two components. Now this component is iron loss component IW and the magnetizing component I mu. Alright, let's discuss about the iron loss or active or working component IW. That iron loss, this is in phase with V1. Now why it is in phase with V1? Because it is associated with only resistive, and in a resistor your current and voltage are in phase. That's why IW is in phase with V1. Now your IW will supply for the iron loss entirely. Alright. Next is the magnetizing component I mu, which is in quadrature with V1. Alright. It is made up of inductive coil. So therefore your current will lag behind the voltage by 90 degree. Therefore there is a quadrature difference, phase difference between them. So I mu current component is wattless. That means it doesn't contribute actively in consuming power. Its function is to sustain or maintain the alternating flux in the core. Now this is the most important point. Okay, the function of the magnetizing component current, it is required. It is not contributing actively to the the active power, but I mu current component, its function is to sustain and maintain the alternating flux in the core. That is the very primary function. So that means current I naught, which is flowing in the primary winding, is a vector sum of IW plus I mu. Okay, clear about the existence of IW and I mu? I mu is the magnetizing current and IW is the iron loss, representing iron loss or active or working component. Okay. So current I naught is a vector sum of IW and I mu. So if I want to draw the phasor diagram of the transformer under no load condition, how will it look like? Now we have a flux phi as a reference, we have drawn it. Let me take a red color. Alright. So let me draw V1. Now remember E1, the EMF E1 and E2. Let's say that we are assuming transformer ratio is 1. So if transformer ratio is 1, E1 is equal to E2. Alright. And E1 and E2 lags behind the main flux by 90 degree. We have seen this before, right? So this is E1 and this is E2. Alright. And since we have in the circuit V2 is open, so E2 and V2 are same. So I write over here V2 is equal to E2, right? Now we have also seen that your E1 and V1 are equal in magnitude but opposite in phase. So this will be V1. Alright. Now let's mark IW. Now IW is in phase with V1. So I'll mark it with blue color. So this is my, okay, first I marked with red one. Alright. So now IW have to draw. IW will be in phase with, let me take a thicker pencil. IW will be in phase with V1 and I mu will be out of phase around by 90 degree. I mu will be lagging behind V1 by 90 degree, let's say. And I naught is the vector sum of IW and I mu. So the vector sum is drawn like this. So this is I naught. Alright. So this is your vector sum I naught bar. Let's represent in terms of bar. So we have V1 bar, V2 bar, E2 bar, E1 bar. Okay. So I naught is the vector sum of IW and I mu. So this is the phasor diagram at no load. Alright. This is the phasor diagram at no load. So from this phasor diagram, why did we choose phi as a reference flux? Now from the phasor diagram, since, let me reduce the font size. from the phasor diagram, since the main flux phi is common, is linking the both, primary and the secondary winding, is common to both the windings. That's why phi is chosen as a reference phasor. As a reference phasor. Okay, it is clear to you. Always in the phasor diagram of all, no load, with load, transformer with load, no load, right? Phi will be drawn as a, will be chosen as a reference phasor. Okay, with respect to that, everything else can be drawn. All right. So from here, the no load power will be given by. So from the phasor diagram also, we can write the following. From the phasor diagram, what all things we can write? It as follows. So what is I0 bar? I0 square given by? I0 square will be IW square plus I mu square. Then what is IW? IW is I0 cos phi 0. And what is I mu? I mu is I0 sin phi 0. Now where it is phi 0? Phi 0 is marked between this. So this is your phi 0. And phi 0 is the phase angle, and cos of phi 0 is the power factor at no load. Okay. So now no load power input will be given by W0, which is V1 into I0 cos of phi 0. Alright, let me put it inside the box. Again I show it to you. I0 is the no load current, V1 is the primary voltage, right? So no load power input will be given by I0 is equal to V1 I0 cos phi. Alright, where cos phi is the power factor at no load condition. Now what will be the iron loss? The iron loss will be given by Wi. It will be V1 I0 cos of phi 0. It will be similar to W0. Why? Because under no load primary input, it's almost equal to the iron loss in the transformer. Why it is so? Because the losses are very very small. Therefore, the input power is also very very small. Alright. So therefore, I naught is also very very small. So therefore, no load input current is practically equal to your no load input voltage or power is actually equal to the iron loss almost. So therefore, both the formulas are same. Alright. Yeah. So that's about it for the phasor diagram at no load condition. If you have any queries, you can post your queries. Yeah. So yeah, that's it for this lecture. Next time we'll start with the phasor diagram of a practical transformer and equivalent circuit of a ideal and a practical transformer. Equivalent circuit of a ideal transformer will be something which we'll be seeing next time. All right. So that's it for today's lecture number 43B. Now some part of 43A was left. Now this I wanted to cover losses in transformer first, and then I come to this differentiation of ideal and practical transformer. So in a practical transformer, there are copper and eddy current losses. In an ideal transformer, there is no loss. In case of practical transformer, there is leakage in flux, whereas in ideal case there are no leakage in flux. In a practical transformer contains some ohmic resistance R1 and R2, right, which we have seen. Whereas in case of ideal transformer, windings consist of purely inductive coil wound on a lossless core. Voltage regulation is never 100%, never 0% in case of a practical transformer, whereas for an ideal transformer it's 0%. efficiency is around 93 to 97% in a practical transformer, whereas it is 100% in a ideal transformer, and all constructed transformer are, or all used transformer are practical transformers, whereas it is impossible to construct a ideal transformer. Okay, so all available transformer in use are practical transformers. All right. Now there was one small query, which one important concept which I wanted to cover. I have written in the form of a question and answer. So the question is, why transformers do not work with DC input? Okay. So here the primary voltage V1 is AC, secondary voltage V2 is also AC, right? Now let's see why. Remember, the direction of current flow is changed in the AC, right? In AC we have, how does the AC look like, right? Let me draw and show it to you. So there is a phase reversal. So current can be positive, negative, voltage can be positive, negative. So whenever a AC quantity flows to the primary winding, that is a current, AC current flows to the primary winding, current is induced in the secondary winding due to mutual induction. Now that's the Faraday's laws of mutual induction, right? But there is no such mutual induction possible when we give input as DC, because in a DC the direction is never changed. This is DC and this is AC. So there is no phase reversal, there is no chance of mutual induction. Therefore, a transformer cannot work with a DC input. That's the same and simple language, the answer to the question why transformer does not work with DC input. Now let's say if you forcefully apply DC as the input. So what will happen? There will be no output obtained at all, first of all. Rather, you will end up heating up the transformer, because there is a resistive, winding resistance. Therefore, your transformer does not allow any DC input to flow through it. And this property of the transformer is called as DC isolation. Transformer only allows AC input to go through and only provides AC output. Okay, so that's the answer to the question why transformer does not work with DC input. So be very careful while answering the question. If they ask you in the exam, it will be for 5 marks, and is the plain answer to it. All right. So now we end the lecture number 43B. Thank you all for joining.